Modern commerce moves on a scale that defies easy visualization. These mega vessels carry upwards of 20,000 containers at a time, each stack weighing hundreds of tons. Despite their massive size, these steel behemoths are entirely blind. Their every movement is directed by an invisible algorithmic formula that humans rarely see and even more rarely understand. Our physical reality is now a trillion-dollar structure resting on a foundation of fragile mathematics. If the math fails, the physical world stops. This pursuit of absolute efficiency has created a single point of failure. When the logic board fails, the entire global supply chain seizes. The realization that our physical infrastructure hinges on microscopic code changes how we define global security. Securing the server room is now as vital to commerce as patrolling the open ocean. Before automation, cargo loading was a manual, high-stakes puzzle. Port planners used physical bay books to track destinations and calculate weights, knowing that a single miscalculation could be lethal. This diagram illustrates the mechanical reality of a hull at sea. When weight is distributed unevenly, gravity and buoyancy create shear forces and bending moments that strain the steel. If these forces exceed the hull's tolerance, a 100,000-ton ship can snap in half. In the mid-20th century, longshoremen had to calculate these immense structural stresses by hand, working against time and the limits of human error. The solution arrived in the 1960s with a mechanical computer, the Cocombs Loadicator. By turning these physical dials, engineers could input cargo data and watch as brass gears calculated exact bending moments. It provided a mechanical guarantee of ship stability. This analog system provided absolute mathematical safety for these massive ships, without needing a network connection or a single line of software. But the demand for digital speed eventually forced us to replace these unbreakable mechanical gears with an invisible, digital brain. As global trade volume surged, analog methods became too slow. Managing thousands of container movements an hour required a level of processing power that humans could no longer provide manually. This era saw the introduction of massive mainframe rooms, moving the central logic of the port away from the docks and into the server. This central nervous system is known as the terminal operating system. Today, platforms like Navis N4 act as the primary intelligence for global logistics. These algorithms dictate millimeter-perfect placement of millions of tons of steel, managing yard allocation and ship stability in real time. Automated cranes and vehicles operate in robotic unison with inhuman precision. The AI instantly calculates shear forces, ensuring every vessel is mathematically balanced. It is a hyper-efficient digital orchestration of brutal physical machinery. We achieved peak efficiency by handing complete control to this software, but we also created a new reality. If the digital brain dies, the steel stops moving. On June 27, 2017, the global supply chain was tested by a total digital failure. A state-sponsored cyberweapon called NotPetya breached the Maersk network. It utilized stolen encryption tools to spread through the system in minutes. The consequences were immediate. Sequentially, 76 global terminals went dark as the malware wiped out their operating systems. Massive automated cranes froze mid-air. Gate systems locked. Thousands of trucks were stranded outside ports as the world's largest logistics network ground to a halt. In a matter of minutes, a company responsible for 1/5 of global shipping capacity lost its entire digital infrastructure. This collapse demonstrated how a microscopic piece of rogue code could effectively paralyze the global economy. This event reclassified digital code as a kinetic weapon, one capable of paralyzing physical infrastructure on a global scale. With their algorithms destroyed, engineers reverted to manual methods. They used physical whiteboards and WhatsApp messages to track billions of dollars in cargo. Restoring the global network required finding an uncorrupted domain controller, a single surviving copy of the network's brain. The recovery was made possible by a localized power outage in Ghana. A single server there had been disconnected from the network when the malware struck, keeping it clean and allowing the company to rebuild. We built an empire of steel upon a fragile digital threat. This same vulnerability exists within the mechanical heart of our power grids,